Hello, thank you for watching my talk, and I make a presentation with this title. So here is the contents. First, I briefly introduce the experiment so-called Hexagon. Then I move on to the main focus of this presentation, which is a test of the clock noise transfer with gigahertz sidebands. This slide includes two more topics in the appendix, so if you are interested, please check them out too. Here is a brief introduction of LISA Phasemeter, which is a circuit to extract an interferometer phase with a digital phase lock loop. A very high dynamic range is required for this because the input signal is very noisy due to laser frequency noise, while we need to extract a picometer signal in post-processing with so-called time delay interferometry. The Phasemeter have several auxiliary functions, but here I focus on sideband PLL, which can measure the differential clock noise. I explain this point more in detail. So here is very simplified phase signal in LISA. So the idea is to subtract ADC sampling jitter from main PLL using piloton, which has 75 MHz. So the point is the piloton itself is driven by a clock on the spacecraft. So the piloton has a contribution of the clock noise. And each spacecraft has its own system clock. So in the whole signals, we have 3 independent clock noises in total. We need to synchronize them. So the way to do it is to embed the clock noise in optical sideband and transfer it to a distant spacecraft. And so here the clock noise is embedded in the optical sideband using EOM. It is transferred to the distant spacecraft, and on the distant spacecraft, the sideband bit nodes is made and measured by Phasemeter in the end. These sideband bit nodes have the information of differential clock noise, and in post-processing we can remove them. And removal of differential clock noise means the synchronization of the system clock. And if you take a careful look at this schematic, maybe you find a hexagonal shape like this. So the hexagon is an optical testbed for the LISA metrology system, which can do so-called optical 3-signal test. This can generate 3 bit nodes pairwise from the 3 frequency sources, which are phase locked to each other. So here, the 3 bit nodes are denoted by phi A, B, C, and they are made from phi 1, 2, and 3. And measurand can be expressed like this with the operator epsilon, which stands for the phase extraction with a metrology system. And by making a linear combination of prime phi A measurand, we can test the linearity of the metrology system over high dynamic range. The current status of the hexagon is like this. The ability to reach a LISA requirement without the clock noise transfer has been already verified in the previous research. So the next milestone is to develop the experimental setup towards the TDI-like topology with a clock noise transfer. But we do not have 3 independent Phasemeters with a proper frequency distribution system at the moment. We came up with the test of the clock noise transfer with a single Phasemeter. Here is the main focus of this presentation. By the way, there is another research related to Hexagon, so-called Hexagon 2. So if you are interested, please also check this talk. So here is the schematic of the experimental setup of the test with a single Phasemeter. I divide this experimental setup to 2 parts. One is optical chain, the other is electrical chain. In optical chain, we simply make optical bit knot between two beams, each of which is phase modulated by independent signal generators. And then the optical bit knot is measured by photoreceivers, and outgoing signal is connected to one ADC card in the phase meter. On the other hand, what happens in electrical chain is to make 1 MHz bit knot between two signal generators. So this have the information of the differential clock noise between them. And here we have one more circuit called frequency distribution module, which can generate 75 MHz pilot tone from 2.4 GHz input. If you are interested in this circuit, please also check Appendix A. So in total, we have this measurement, optical chain and electrical chain. And in the optical chain, we can measure the dynamics of a carrier-carrier bit knot with main PLL, and with sideband PLL, we can measure also the carrier-carrier bit knot and sideband dynamics. And in electrical chain, we can measure the reference for the differential clock noise between the two signal generators from the 1 MHz bit knot between them. So the idea is to make the signal combination like this. First, the reference for the differential clock noise is subtracted from sideband PLL. Then the residual is further subtracted from the carrier dynamics. And this, it should be noted that the upper and lower sideband has the opposite sign of the differential clock noise. And this combination can be further expressed like this. So, because the sideband dynamics is expected to transfer the differential clock noise properly, these two terms are expected to be cancelled. And the residual noise is the difference between carrier and the carrier, which should be very low because the dominant noise source in this residual noise is just electrical noise like the phase meter or power splitter. So here is a result. So there are several results which are remarkable. But first, I want to stress that differential clock noise could be transferred by the gigahertz sideband more or less, which was shown by green and yellow. So green is the signal combination before the subtraction of the reference for the differential clock noise. So these two coincide with each other well here. And after the subtraction of the differential clock noise, we could get the suppression by 6 orders down to Cn. But we are still 2 orders above the expected level, which is shown with red. Hence, we did further analysis of Cn. So 3 more plots are shown in this figure. Dark Cn is just a counterpart of Cn with a lower sideband. And magenta is the combination which can be generated only from the optical chain. So in principle, there is no noise contribution from electrical chain. On the other hand, the navy combination focuses more on electrical chain, which can act as a diagnosis of clock noise subtraction. So here I stress only the biggest problem we currently have, which is the fact that magenta doesn't meet the requirement. So as I said, magenta is not related to electrical chain, means there is no noise contribution from the clock noise subtraction. This is already a good hint towards an issue with the optical chain, like the noise, something wrong happens around EOM or Phasemeter, which is placed in the end of optical chain. So it was the current status of this test. So here is conclusion and next step. So after removing the noise related to the optical chain, which was identified in this experiment, we move on to the next test with multiple Phasemeters. So again, thank you for your attention. And if you are interested, please also check appendix for 2 more topics and related talks. Thank you very much. Bye-bye.